Well, if we're going to spend a lot of time looking at water chemistry, it probably behooves us to start by looking at the simplest possible case. And the simplest possible case that we can look at is a case of having a bucket of water and wanting to know about the equilibrium associated with whatever's in there. So if I go ahead and draw a bucket of water here, and it looks like this, and I've got my water here, I can ask myself, what is this stuff doing as it sits here? Well, at that point, you have to ask, are there a variety of different kinds of chemical reactions that might take place that actually involve water? Well, we know of one right off. There's this reaction that involves water and an exploding hydrogen balloon. That's this example right here. This right here is an actual chemical reaction. It's a combustion reaction written going in the left direction, in which hydrogen gas and oxygen make water. Written in the forward direction, this could be a remarkable opportunity for us. If we could find some sort of energy that came down here, heck, maybe energy coming from the sun or something, that would be doing this thing we call splitting water, making hydrogen gas and oxygen, then you have produced what is otherwise a very thermodynamically unfavorable process. You have produced a bunch of hydrogen and oxygen, and then you can allow these to react to drive your car or power a space shuttle in a very nice, clean energy sort of way. So that's a wonderful kind of reaction. It's definitely worth studying. We spent a lot of time looking at it in the fall when we were doing thermodynamics, and it has nothing to do with what we're going to be talking about here. I show you this, though, because people often confuse this particular reaction here with the one I'm going to show you, which is the reaction that is the title of today's lecture, the autoprotolysis, the autodissociation of water. The second I say the word auto, what that is suggesting then is that it involves water by itself, and to say that it dissociates or it protolyzes means that it's making ions. It's making protons and hydroxides. So here's the reaction we're concerned with. Water going to make protons, water going to make hydroxides. This fundamental chemical equilibrium is going to be present in absolutely every chemical system that we look at as long as we're doing water chemistry for the next couple of months. This will always be lurking in the background and will always be pretty darn profound as an equilibrium for us, in that we're going to have to consider, is it important? Can I treat it as being negligible in terms of its contributions? But in the end, being able to talk about the amount of this, or the amount of this, the amount of protons, the amount of hydroxides, is going to be key to all of these lectures coming up.